Hello, welcome. My name's Dr. Phil Winder. I'm the CEO of Winder.ai. In this presentation, I'm going to be talking about RAG architectures. And just before we get started, a little bit of admin. If you'd like to ask any questions, then please feel free. I'll answer all of the questions at the end. If you just pop a comment in any of the platforms that you're using, I should be able to see it. Hopefully, you find this talk enjoyable. And if you've got any extra questions that don't really fit into this presentation, then please feel free to email us at winder.ai. So phil@winder.ai is my email, or you can visit the website to find out more contact details. Okay, so the presentation today is about retrieval augmented generation, RAG, and specifically the implementation patterns and architecture patterns of various RAG systems that are prevalent in the literature today. To reduce the scope of this presentation, I won't be talking about implementation details or show you how to do anything. If you're interested in that level of detail, then please get in touch to show your interest, and I'll be happy to do something like that in a future webinar. Although I don't go into the technical details, there still is a lot of terminology used, and therefore this is quite an advanced topic. So feel free to ask questions if you don't understand what something means. But this is kind of intended for a slightly more advanced audience. Okay. In the past year or two, as I'm sure you're aware, generative AI techniques have taken a step towards human level performance. Models like the GPT series, Stable Audio, Stable Diffusion, and Sora have tackled various modalities with great success. But AI-generated content continues to suffer from well-known challenges, like maintaining up-to-date knowledge and incorporating niche subjects, and crucially, for business purposes, integrating proprietary data. Retrieval augmented generation, or RAG, is one proposed method to alleviate many of these challenges. It works by incorporating an external repository of information. This information can be used in a variety of ways to improve the input to the generation or the output. So the purpose of this presentation is to present a high-level overview of some of these architectures. A typical high-level RAG architecture is shown here, split into 4 boxes: the input, the output, the generator, and the retriever. So let's talk about each of those in turn. First, a user provides an input query or a prompt. The prompt can be a combination of modalities. Modality means the type of content that is used. For example, text, image, audio, video, or even domain-specific data like scientific or 3D data. They're all types of modality. In this presentation, I'll mainly focus on the text-to-text modalities, since RAG became famous for this modality first. But RAG has already been adopted across various modalities and domains. But nevertheless, I will stick to text-related terminology to simplify the language of the presentation. Second, the input is passed to a retrieval module. The retriever's goal is to provide extra context to the user's query. The information obtained from the retriever can be incorporated in a couple of different ways, and I'll talk about this a lot more later. A simple mental model of what a retriever is to think of it as a search engine. If you're asking for the most relevant results to the user's query, so imagine it's DuckDuckGo or something like that, and you're retrieving the top 10 results for the user's query. These queries can then be passed in to the generator, or they can augment the output, or you can augment the input. In general, there are 3 categories of retriever. Sparse retrieval is the most traditional form of retrieval, where content is indexed and statistics are used for comparison. So TD, IDF, query likelihood, and BM25 mechanisms are common. Dense retrievers are methods that represent content as embedded vectors. For example, a section of text is converted into a dense numerical representation, and then to find relevant results, we use a nearest neighbor-like algorithm to find it. And then there's also a third category, which represents all of the novel, often domain-specific techniques. For example, optimizations using trees or knowledge graphs, could be constructed from the content, and then a graph search could be used, for example. Irrespective of the methodology, the whole purpose of the retriever is to find relevant information and provide it to the other modules. Third, the input is, and some combination of the retrieval results are passed to the generator. Of course, the most famous generator is the transformer model. And if you'd like to learn more about that, then I recommend you check out one of our older articles about GPT in particular. I've just put the link up at the top there, winder.ai/GPT scratch. But there are other common technologies too. Diffusion is probably the next biggest technology, whereby noise is gradually added to the data until it becomes random, and a model is trained to reverse that process. The reverse model is then conditioned over a user prompt and is capable of generating novel content. This process works really well for images, videos, music, and even molecules. We've had examples of material science type applications. For data that is more inherently sequential, transformers tend to work better. There's also generative adversarial networks as well, or GANs, which were a precursor to transformer models. Were a precursor to the diffusion technique. They use a second model called a discriminator to predict whether the data is real or fake. This information is then iteratively fed back into the generator to improve the generation of content. And there are models too, like the LSTM, which is a form of recurrent neural network that can be used as a generator, but they aren't as popular these days. The point is, again, there's a wide range of potential generators that you can use in these architectures. And finally, the final step is to provide the recombined output to the user. Your RAG system could produce multimodal outputs, like we mentioned before, but for the purposes of this talk, imagine the output just being text. So, researchers and practitioners have proposed a wide variety of ways of incorporating the retrieval results. I've summarized them into 4 categories. We've got altering the input, latent representation within the generator, altering the output, and speculative. Okay, just going to take a moment to breathe and check if there's any issues or comments. Nope, all good. Okay. The first method. The idea here is that the user's query is augmented with the retrieved documents, with the retrieved results. So this is also called query-based RAG or prompt augmentation. This is one of the most common forms of RAG that you'll see. Once documents have been merged with the user's query, this is subsequently passed to the generator as the prompt. The second method, similar to the first, uses latent representations of the document instead of raw text. So here we're converting the query and the we're not converting the query. We're converting the retrieved documents into a high-dimensional embedding, and they are used directly by the generator to better condition the response. This method works really well when it is difficult to pass raw data to the generator. For example, if you need to pass an image or another complicated piece of data. However, these are generally more difficult to use because of the direct injection of the embeddings. It's quite an invasive procedure. The third method uses retrieval results to alter the output of the generator. This is also sometimes known as logit-based RAG. So here we're directly affecting the logits, which are the last stage in the deep neural network of the generator model. So the output-based RAG techniques, they alter the probability, ultimately. They alter the probability of choosing particular words according to the retrieval results. So this works well when the outputs must be conditioned according to some logic defined in the repository, like when generating code, for example. And finally, speculative RAG attempts to find opportunities to replace the need for generation with the result of the retrieval itself. And the whole purpose of this is an optimization to reduce resource usage and latency. And as you might imagine, there are optimizations to each of these stages that you can perform to improve results. Note that many of these optimizations are domain and use case dependent and can be used in combination. You can improve the input by transforming the user's query. For example, you may blacklist words. You can also improve the quality of the data being indexed by the retriever. For example, all of the usual data quality tricks are useful here. You might even add extra context or metadata. You could improve the retriever in many different ways. All of the retrieval specific literature is up for grabs. You could recursively retrieve information. You could optimize chunk retrieval. You could fine tune the retriever. You could use metadata like local results and re-ranking models and many more. The generator could be improved by fine-tuning the underlying generation model, or you can improve the system prompt with known techniques like chain of thought, greater expressiveness, conditioning, and others. Altering the hyperparameters of the model as well, both statically at compile time and dynamically at runtime. You can also alter performance. The combiner can be improved by adding a routing layer that possibly combines the result or forwards the request to another agent. Rewriting uses a combiner to add further actions. Reprompting is a recursive technique that happens before generation. And finally, you could improve the system as a whole. You could iteratively feed the result back to the input to improve the final result. You could also include feedback mechanisms to fine-tune the various trainable parts of the system. So as you can see, there's a lot to alter, but what should you try and which should you try first? So let me try and provide some advice on what architectures are the easiest to implement and operate, and which improvements are the best to try first. So let's look back at the high-level architecture. Of all of the components, the interfaces to the outside world are generally the hardest to change. This is because many retrieval systems and generators only work with specific modalities. So make sure that the interface and indeed the problem definition is clearly defined first. This should also indicate what modalities you're working with and make sure you don't change them halfway through. Next, the generator is becoming easier and easier to swap out. Experimenting with different generators is likely to be a great source of improvement, whether that be for performance or resource optimization. The retriever is likely to end up as the most bespoke part of your RAG system. You'll probably begin with a swappable framework, but as you make improvements, it's likely that it will get harder to change. So what about the RAG architectures? Which is best there? If you're interested in playing with the different RAG architectures, then I'd recommend all except the latent representation approach. This is because it's the most invasive and destroys the generator interface. Like I said, it's injecting prompts directly. It's injecting embeddings directly into the generator. If you're having to do that, then you have to match the embedding mechanism and the embeddings that you've generated with the generator. That makes it harder to swap out the generator because you've got to pick a very similar a generator with a similar interface. However, if you must incorporate multimodal inputs, then this might be the only choice. Altering the output of the generative model with the retrieval results could also be invasive, but that depends how you do it. So I'd suggest that augmenting the input is probably the most common and the easiest RAG implementation to implement. Also, it's the easiest one to improve over time. And that's followed by 2, the speculative one, which is more of a high-level optimization of the whole system. So what about the individual improvements to the specific components of the RAG architecture? Well, everything in green here represents an external setting that are directly under your control in any RAG architecture. Changes to any of these elements will cause the least harm. For example, altering the system prompt, hyperparameter tuning, prompt transformation, that's all fully within your control, very easy to change, very easy to try. So I recommend starting with that. Items in yellow represent more invasive changes that typically involve training your own models or customizing certain pieces of the puzzle to act within the RAG architecture. For example, you can do re-ranking on the retriever. To do that, you need to train a model to do optimal re-ranking for your use case. So it's important. You can use re-rankers off the shelf, but again, they won't be optimal for your use case, especially if your use case is more niche. In that case, you will need to train your own. You can also do things like fine tuning of the generator and such. And by the way, if you're interested in fine tuning the generator, then you can check out one of our products called Helix, which makes it really easy to fine tune generative AI models in the cloud and on your own hardware on premise. So check out tryhelix.ai. Finally, the items in red represent the most advanced efforts to improve performance. These are generally higher level architectural concerns that directly affect RAG performance. Okay, just before we wrap up, I had one question just before the talk started, asking more about the scalability concerns in RAG systems. So it's slightly out of scope, but it was such a good question that I thought it might be useful if I add a click slide here. So before you start optimizing your solution, first make sure you know the problem that you're trying to solve. There's a common phrase that boils down to measure first, optimize later. The problem could be that you can't index fast enough, or that latencies are too high, or maybe you have users on different parts of the planet. Depending on the problem, each of these has a particular, a different implementation, and they're all massively different as well. So make sure you get the problem right first. Next, consider there's a simpler alternative to your problem. Regular old-fashioned search is already highly optimized and a mature technology. Your use case might be able to leverage those technologies in conjunction with LLMs via function calling, for example, or maybe you don't even need an LLM at all. So consider if there's a simpler alternative. But if I had to pick one particular scalability problem, probably the most common bottleneck is concurrent users. So scale in this sense means scaling vertically to add more resources to your systems or horizontally to handle the concurrency. Again, you should always measure first, especially to find out which part of your system requires optimization. But in these architectures, it's often the generative component that must be scaled first, since they tend to they tend to be very resource hungry and only handle one or a few concurrent users at a time. So eventually, you'll need to be able to scale the retrieval component as well. Probably those systems can probably scale vertically at first, and then you need to start worrying about scaling horizontally. How you actually do the scale depends on your underlying compute platform you're using. We mostly use Kubernetes, but that's for more sophisticated deployments and more mature businesses. But scaling on a managed service is probably easier if you're wanting to avoid the operational burden. You can also scale by optimizing your solutions as well. So, for example, if you're currently relying on a third party for all of your LLM calls, then you might consider hosting your own models, locally close to the rest of your system. Another idea is if you can replace or get away with a less capable language model, a small language model, instead of a large language model, then you could serve multiple concurrent users for the same cost. We just released a new blog post today on small language models that you might be interested in. The link is there at the bottom, winda.ai/SLM. Okay, final thoughts. So RAG is a useful architecture for incorporating knowledge into generative AI. But remember that fine-tuning is also a viable alternative. So investigate that too. It is for pure performance. It's not quite as good. But if you are working in a niche domain, then it can be advantageous to learn the concepts in that domain, which so if you watched one of my previous webinars, we demonstrated that the combination of RAG plus fine-tuning outperforms RAG, but only by a marginal amount. But I think that's very dependent on the particular domain that you're working in. So yeah, consider that. And it's also important to remember that when I say retrieval, we mean the use of any external data. So data from databases, from APIs, from search engines. The retrieval problem might actually be the biggest challenge you face here. So probably best to focus your efforts there. And the reason why I say that is because when we talk about RAG, we're often pushed towards using vector databases, basically indexing content into vector databases. But you can retrieve that content from anywhere as long as it's got some kind of API. So it doesn't necessarily have to be a vector database. Just bear that in mind. And I've tried to present the current variation in the RAG architectures that you'll see today, and a wide variety of potential improvements that I recommend you research if you're interested in any of them. And with that, I'll stop there. If you're interested in topics like these, then please feel free to sign up to our newsletter on our website. We've got more events in the future. You can view the events page on the Winda AI website to find out what's coming next. And with that, I'll have a pause and then answer any questions. Thank you very much. Okay, first question. Thank you very much, Biju, for the question here. Appreciate you joining us today. So the emerging consensus is that a knowledge graph is essential for accurate RAG retrieval. What are your thoughts on this? I'm not sure that it's essential. I wouldn't say that. It depends very much on this is very much a retrieval problem. So basically what you're trying to do is for your use case, for your users' queries, for your domain, what is the best way of obtaining the most relevant information for your problem? And for many problems, a simple vector search, a simple nearest neighbor search is likely to be, it's likely to work really well. But there's also applications that are maybe more focused towards knowledge bases, like Q&A applications specifically for knowledge bases, where I can definitely envisage that a graph-like structure that incorporates facts as being more efficient. So for example, imagine that you are working for a vendor that's selling stuff to nuclear power plants, and they're wanting to understand they're wanting to ask questions about the specific specifications of parts for the nuclear power plant. It's vitally important that you get those specifications correct. So it might be advantageous there to curate a knowledge base with correct factual information, and your retrieval module can leverage that graph-like structure in order to provide the relevant context for the user's query. Compare that with a vector database based approach where you're attempting to index raw text. You're going to get a big blob of text where buried within that data sheet is some table or something. It's probably not going to be very efficient at indexing that data. So Yeah, hopefully that's a good example. And I think the answer to that is that it's not essential, but it might be if your use case requires that kind of information. Good question, though. Any more questions before we stop for the day? I'll just give it another minute for any more questions to come in. I know there's a little delay. Okay, no more questions. So we'll call it there. I appreciate you joining us today. If you've got any more questions, then you can reach out to phil@wind.ai. Otherwise, I will see you next time. Thanks a lot. Bye-bye.